In my previous video, I managed to balance this turbine rotor down to milligram accuracy, but that was only single plane balancing. A real turbine requires dual plane dynamic balancing. And this is not just repeating the same measurement twice. The physics is coupled, the math is coupled, the errors are coupled. In this video, I'll show you how I upgraded my DIY balancing machine to handle two planes properly, including all the problems, failed attempts, and the final working solution. Hi, I'm Alfonso. I spent more than 40 years working as an engineer in the space industry. Now I apply that experience to CNC machining and DIY turbine engineering here in my workshop. Mechanically, the upgrade is simple. The structure is still based on 3D printed components and low-cost bearings. The main difference is sensor integration in both planes. As always, I've left the 3D models in the description if you want to build your own version. For proper dual plane balancing, I need one accelerometer per correction plane. One on the turbine disk side, one on the compressor side. My first idea was simple. Connect both BMI 160 sensors to the same I2C bus. In theory, it should work. In practice, it didn't. At 1600 Hz sampling rate, the bus bandwidth was not enough. I simply couldn't read both sensors reliably. I then tried switching to SPI. After several attempts, no results. If anyone has solid SPI experience on low-cost ESP boards, let me know in the comments. The final solution was using two independent I2C buses on an ESP32S3, but even then, the standard BMI 160 library didn't support dual bus operation. So I had to move to the wire library and implement low-level communication manually. The final firmware runs both I2C buses at 1600 Hz. Each signal goes through a second-order Butterworth bandpass filter. Lock-in detection synchronized with rotor speed, averaging over 3,200 samples. If the RPM stays inside a predefined window, the system outputs stable amplitude and phase data every 2 seconds. I've left the full source code in the description if you want to review it. Time for the first real test. I added a 3D printed support for the airgun to improve repeatability. The turbine side readings were extremely stable, but the compressor side sensor was noisy, very noisy. After some investigation, I discovered the problem. The compressed air was flowing directly over the accelerometer and wiring. Turbulence was injecting mechanical noise into the sensor. The solution was simple but effective. A 3D printed airflow barrier in front of the sensor. After installing it, measurements became dramatically more stable. Next step. Identify the most stable measurement window. Measurements near structural resonances are useless. After testing multiple RPM ranges, I found that between 4,800 and 5,000 revolutions per minute, the system response was highly repeatable and free from resonance amplification. With stable measurements, I moved to system offset calibration. I placed a known mass at 0 degrees and measured the detected angle. The difference is the system phase offset. After several repetitions, I noticed a slight speed-dependent variation. I approximated it with a linear regression. and implemented automatic offset correction inside the firmware. Repeating the mass test after correction produced an angle very close to 0. That confirmed the calibration was successful. In single plane balancing, the vibration can be modeled as a single complex vector. One correction mass produces one proportional response. But in dual plane balancing, the system becomes coupled. A correction mass in plane A generates vibration components measured in both plane A and plane B sensors. The same happens for plane B. Assuming linear behavior of the rotor system, we can model the response using influence coefficients. The system can be expressed as VA and VB are the measured complex vibration vectors. MA and MB are the correction masses, and alpha are the influence coefficients. By performing 3 runs initial, test mass in A, test mass in B, we experimentally determine the matrix coefficients. Once the matrix is known, we simply invert it to calculate the required correction masses. In theory, it's just linear algebra. In practice, measurement noise makes it much more interesting. The system required 10 milligrams in plane A, 26 milligrams in plane B. After applying those masses and repeating the procedure, the second iteration calculated only 3 milligrams in both planes. That's already within my target precision. The final step was grinding the equivalent correction mass, 180 degrees opposite to the detected heavy spot. Dual plane balancing is significantly more complex than single plane. It requires mechanical stability, clean signal acquisition, proper filtering, careful calibration, and correct mathematics. But with this DIY machine, I believe I can now properly balance my RC turbine rotor. Is this the end of the story? Probably not. I'm very curious about piezoelectric sensors, and there are still many improvements possible. If you found this useful, consider subscribing so you don't miss the next stage of this turbine project. Thanks for watching, and see you in the next one.